Equipping a massive commercial facility with a large-scale solar array requires hundreds of individual solar panels and extensive mounting hardware to complete the grid. Before installation can even begin, crews face a specific logistical requirement: physically lifting all of those required materials from the ground up to the active, elevated workspace on the roof. This video shows a crane as it swings a fully stacked pallet of solar panels toward a drop location. Consolidated tightly onto a single wooden base, the localized weight of this material routinely exceeds 1,000 kilograms. By design, an average commercial roof is engineered to support light, widely dispersed environmental loads, like a layer of rain or a heavy gust of wind spread out across thousands of square feet. Suspending a concentrated 1,000-kilogram construction pallet in the air and dropping it onto that same surface introduces a highly localized force that falls entirely outside the building's original design parameters. When installation crews place these extreme localized forces onto a roof without prior structural analysis, the physics of the material take over immediately. Look at the impact zone in this photograph. The dense point load easily compromises the corrugated metal, punching through the sheeting. Panning down into the breach reveals the secondary failure: internal support purlins and rafters snapping beneath the weight. Engineers define this exact catastrophic structural event as an ultimate capacity failure. Avoiding ultimate capacity failure means identifying highly specific, temporary drop zones directly over the building's strongest primary structural elements. It is physically impossible for a human eye to identify these safe zones simply by looking at a flat expanse of roofing material. Preventing a catastrophic roof collapse requires precise, rigorous data analysis long before the crane ever arrives on site. A common industry assumption suggests that if a roof can safely hold a massive 100-kilowatt solar array for 20 years, it can certainly hold the materials used to build it. This 3D diagram demonstrates a distributed load. Finished panels spread their mass over a massive area, resting across dozens of rafters. But watch when an isolated 1,000-kilogram block drops onto a single point. The purlin underneath flashes critical red, bowing heavily downward under extreme pressure. When localized point loads exceed their engineered limits, standard roof purlins stop acting as supportive elements and instantly transform into critical points of failure. Despite these clear physical limits, installers frequently rely on a quick walk across the roof to verify its structural readiness. This is a dangerous procedural habit. The human eye cannot penetrate corrugated sheeting to extract the vital structural data required for a heavy load drop. First, visual inspections cannot determine the exact type and gauge of the structural connections locking the subframe together. Second, walking the roof entirely obscures the precise weld specifications and manufacturing tolerances applied to critical joints. Even conducting an internal inspection from the warehouse floor looking up is often useless, as fireproofing sprays or thick insulation bury these microscopic details. Those invisible connection types and welds strictly dictate the maximum physical stress a joint can endure before it shears apart. Without extracting that exacting data, any calculation regarding roof load capacity is missing its core variables.
It becomes a guess. Physical inspections are excellent for spotting surface rust or worn sheeting, but they fail completely to map the structural thresholds required to survive a 1,000-kilogram impact. To safely calculate a drop, engineers require the building's original structural drawings as an absolute, non-negotiable prerequisite. This detailed structural blueprint provides the exact hidden variables missing from a visual inspection. It explicitly lists the required weld specifications, material gauges, and connection tolerances buried inside the frame. Engineers extract this raw schematic data and translate it line by line into a highly accurate digital simulation. They utilize advanced structural modeling software called Spacegass to simulate how the building's physical materials will react to extreme temporary weight. Every unique structural element of the building, such as the exact dimensions of custom portal frames, must be accurately programmed into the Spacegass environment to reflect reality. Original structural drawings provide the specific data points required to transform a physical guessing game into a predictable mathematical model. The primary objective of running the Spacegass simulation is to comb the roof's geometry and map out verified, completely safe drop zones.
In this digital simulation, you can see the software running targeted stress tests. It isolates and maps these drop zones almost exclusively over the strongest primary structural nodes, like the main portal frames, highlighting them in bright green. Finding a structurally safe node is only the first step. That data must be reconciled with the crane's logistics. The crane's strict reach limitations and maximum drop angles are cross-referenced with the mapped drop zones to verify placement is mechanically feasible. But there is a final caveat. Even when targeting a calculated drop zone, a massive point load can never be placed directly onto the bare roofing materials. This requires the use of physical hardware, known as spreader beams. Looking closely at this wireframe, notice how the pallet rests entirely on the horizontal spreader beams. Engineered to a precise size and length, these beams physically force the pallet's weight to split and distribute evenly downward across multiple supporting rafters. Successfully landing a pallet requires the alignment of 3 distinct variables: exact structural model data, rigorous crane capability limits, and proper spreader beam distribution. When executing a commercial solar installation, there are only 2 potential structural outcomes for the roof. This video demonstrates the failure state. Treating pallet logistics as an afterthought, relying on physical walkthroughs, and bypassing load distribution protocols results in structural damage. The success state relies on precision. It requires lowering heavy loads specifically into mathematically calculated drop zones, mediated by properly sized spreader beams. Standard commercial roofs are structurally incapable of supporting concentrated 1,000-kilogram point loads by default. Skipping formal procedural load analysis directly gambles with the integrity of a multi-million-dollar physical asset. Commissioning a comprehensive pallet load assessment rooted in original structural drawings and advanced Spacegass modeling is the single non-negotiable requirement that guarantees the facility survives the installation process.